In this video, I want to show you a model that is commonly taught in physics and chemistry classes. The model describes the composition of a gas, and the formal model allows us to derive a number of well-known laws about the behavior of gases. The question I want to ask is, does confirming the model's predictions give us reason to think that the assumptions of the model about the fundamental constituents of the gas are true? We've looked at this question before, but with this example, there are some particular lessons that I want to highlight. This model, or theory, is known as the kinetic theory of gases. Before the modern 20th century understanding of atoms and molecules, we had a number of atomistic theories that posited that matter was composed of tiny particles, too small to see, that are constantly in motion, and this hypothesis was used to explain macroscopic properties of matter. The kinetic theory of gases is just one such atomistic theory. The word kinetic just means motion, so the name is referring to the assumption that a gas is composed of particles in constant motion. Let's look at the core assumptions of this model of a gas. Number one, gases are composed of a large number of particles that behave like hard, spherical objects in a state of constant, random motion. Number two, the particles move in a straight line until they collide with another particle or the walls of the container. Number three, the particles are much smaller than the distance between the particles. Most of the volume of the gas is empty space. Number four, there is no force of attraction between gas particles or between the particles and the walls of the container. Number five, collisions between gas particles or collisions with the walls of the container are perfectly elastic. Now, what does perfectly elastic mean? It means that no energy is lost during a collision. Kinetic energy, energy of motion, can be transferred from one particle to another during a collision with no loss. So the total kinetic energy of the particles after a collision is the same as it was before the collision. That's a perfectly elastic collision. So just to clarify, when you see a ball bouncing, when the height of the rebound gets smaller and smaller, that's because the collision between the ball and the surface is not perfectly elastic. Some of the kinetic energy of motion gets converted into different forms of energy when the ball is compressed, when it hits the surface. Both the ball and the surface that it contacts actually heat up a bit. That energy is no longer available to be converted back into kinetic energy, so the ball won't bounce as high on the rebound. With a perfectly elastic collision, in principle, the ball would keep bouncing and returning to the same height forever. So that's the assumption we're making. The particles are perfectly rigid spheres, and their collisions are perfectly elastic. And finally, assumption number 6, the average kinetic energy of a collection of gas particles depends on the temperature of the gas and nothing else. So this model is designed to show how the macroscopic properties of a gas, like pressure, temperature, and volume, can be understood and analyzed in terms of the motions and collisions of the particles that make up the gas. It can also be used to analyze macroscopic properties like viscosity and thermal conductivity of gases. The pressure of a gas, for example, is analyzed in terms of the force exerted by the particles hitting some unit area of the surface of the container. Similarly, the temperature of a gas is analyzed in terms of the average kinetic energy of the particles. Temperature turns out to be a measure of the energy of motion within the gas. Now, with this model, you can formally derive a number of empirical relationships that can be tested, like this, the so-called ideal gas law. Pressure times volume is equal to the number of moles of the gas, N, times a constant, R, times the temperature. So, for example, if you were to hold the volume constant and raise the temperature, the pressure should increase, which it does. Within a range of normal conditions, and for gases that aren't too dense, the ideal gas law gives pretty accurate results. So now let's get back to these model assumptions. What are we to make of them? Well, the first thing to note is that some of these assumptions are clearly false. The molecules of a gas are generally not spherical, and they're certainly not solid. The collisions between particles and between particles on the walls of the container are not perfectly elastic. The model assumes that there are no forces acting between the particles, but the gravitational force is always there, and we know that there are other quantum mechanical forces that are present. So how should we think of this? Does the empirical success of the model give us reason to think that these assumptions are actually true? No, we have a better way of analyzing this now. The success of the model is explained by the fact that the differences that we just noted, the differences between the properties of the particles in the model and the properties of actual gas molecules, don't matter to our reasoning within a certain domain of application. Our model abstracts away the differences that don't make a difference. Remember, in our general picture of the modeling relation, what I'm calling the abstraction hypothesis has two parts to it. The first part is the claim that the similarities between the model and the target system are relevant to the kind of inferences we want to make with the model. And the second is the claim that the differences that the model ignores are not relevant to the inferences that we want to make. So, what the predictive success of this model shows is not that the model's assumptions are in fact true. The assumptions are still false. What it shows is that the abstraction hypothesis is justified. What it shows is that we have reason to believe that these two claims are true. That the analogy we're drawing between the model and the target system captures the similarities that are relevant to our reasoning and ignores the differences that are not relevant. When the abstraction hypothesis is justified, we say that the model applies or is applicable. This is how we define a domain of application. So when gas temperatures get too low or pressures get too high, the predictions of the model deviate from the observed behavior. And we say that the model no longer applies in this domain, because these are conditions where the differences that the model ignores actually do matter. And consequently, the abstraction hypothesis is no longer justified. I think this example illustrates a couple of important points about scientific reasoning. 1. A false model can generate true predictions. We've already made this point, but here I want to highlight that many of the models that scientists use today successfully to solve problems and explain and predict observations employ assumptions that everyone recognizes are strictly false. A corollary to this is that the empirical success of a model, its predictive and explanatory success, does not prove that its assumptions are true. On the contrary, many successful models in science are successful precisely because the assumptions they make are idealizations that we know are false. But the idealization captures something important, something relevant to the actual phenomena, and thereby makes it possible to extract the information that is relevant for drawing reliable inferences about the phenomena. This feature of mathematical modeling is widely understood by those who practice it, enough that there are running jokes about it. The phrase, "consider a spherical cow," is part of the lore of modeling. It comes from a joke that makes fun of the simplifying assumptions that are sometimes used in physics. A dairy farmer wants to raise milk production for his cows, so he asks a local university for help. After a week, a physicist from the university visits the farmer and says, "I have a solution, but it only works in the case of spherical cows in a vacuum." If you Google this phrase, you'll find lots of images of spherical cows. This textbook by John Hart is on modeling techniques in environmental science and ecology, and it plays up the role that abstraction and simplification play in revealing patterns that are embedded in the natural variation that we see in nature. And that's the key here. That's the secret. These idealizations, these simplifications, these abstractions, though often strictly false, make it possible to identify the key variables and the patterns that are essential to explaining phenomena in nature. Unfortunately, these features of scientific reasoning are hard to understand if we focus too much on the question of whether a theory or model is true or false. Usually, that's not a helpful question. Even our best theories are false in some respects. This is why scientists are often uncomfortable answering this question. The better questions to ask, the more useful questions, are these. Within what domain and under what conditions does the theory or model make accurate predictions about the world? And within what domain and under what conditions does the theory or model fail to make accurate predictions about the world? These are questions that scientists are comfortable answering, because these are the questions that are actually relevant to how science is practiced. Now, if your question really is, what does this theory actually say about the world? If it's true, then, as I argued in the previous video, what you're really asking is a philosophical question about the interpretation of a theory. This is not a question that most working scientists are well trained to address, for the reasons that I've argued. What working scientists are well trained to answer are these questions right here.